called Halley's Comet. The encounter, it's on from 11 o'clock to half past midnight.
A scientific and television history in the making, as Patrick Moore sets the scene for tonight's celestial encounter.
Good evening, and welcome to our Night of the Comet. Within the next hour or two, we may learn more about Halley's Comet, our most famous cosmic visitor, than we've done since the start of human history. I'm afraid you won't see the comet properly at the moment, but from the southern hemisphere, it's a wonderful sight, with its tail stretching across the sky. And here's the latest picture of it, seen from Siding Spring in Australia. Thanks to modern technology, we can now get close-range views of it. Whether we're going to see the actual nucleus is open to question, but whatever we do see will be of tremendous scientific interest and importance. The European Space Agency is sending its first deep space probe, Giotto, right into the heart of the comet. Something that's never been done before. This is a picture of Halley's Comet being sent back now by Giotto. Let me stress that those colours are not genuine. They indicate differences in brightness and therefore differences in density. And undoubtedly the mysterious icy nucleus is somewhere inside that patch that shows up on your screen as being blue. The object of tonight's mission is to follow Giotto all the way in. At the present moment, it's something like 250,000 kilometres away from the nucleus of the comet. At closest approach, in just over an hour's time, it'll only be 540 kilometres away. And it's then, if at all, that we're going to see the nucleus. We've simply got to wait and see. Halley's Comet is named in honour of the second Astronomer Royal, Edmund Halley. His headquarters was at Greenwich, at the Royal Greenwich Observatory, where James Burke now is. James.
Thank you, Patrick. Well, I'm here on what is a bitterly cold night at Greenwich because it was here, in a sense, where the original scientific interest in the comet Halley really got going. And I'm here especially to look at the technology behind tonight's literally once-in-a-lifetime encounter, the encounter between the spacecraft Giotto and the comet called Halley. That we are able at all to rendezvous with a comet travelling at 68 kilometres a second, 230 million kilometres out in space, is mainly due to the original predictions by Edmund Halley, England's second Astronomer Royal, here some 300 years ago. The latest of his successes is with us tonight, here in the Octagon Room, where the earliest observations were made. Professor Sir Francis Graham-Smith, the 13th Astronomer Royal, is watching these events with his guests, who include Professor Alec Boxenberg, Director of the Royal Greenwich Observatory at Hurst-Wonsow, and other experts in what we'll loosely call tonight cometry. We'll be talking to them later. As Giotto races towards the encounter at about 70 times the speed of a bullet, I will be taking a look at the onboard instruments, and in particular at that camera that we hope will answer fundamental questions, not just about Halley, but perhaps about the origins of the solar system and even the origin of life on Earth. I say we hope for two good reasons. One, Giotto may not survive the journey to the heart of the comet to take those first ever pictures of its nucleus. And two, even if it does, the pictures that the two Russian spacecraft that went past the other day made it all look pretty dicey. The situation as they saw it makes us feel that tonight the encounter may turn out to be a more dangerous event than was perhaps foreseen. But more of those problems later on, because right now the spacecraft is heading into the comet's coma, a giant cloud of gas and dust surrounding the nucleus. And since Giotto's encounter speed is about 240,000 kilometers an hour, every tiny dust particle will hit Giotto like a bullet. This is what the spacecraft looks like as it heads for Halley, like this with its dust shield forward. And as we go through the evening, I hope we will be able to see the build-up of computer-generated data showing the dust impacts actually hitting the shield at the time. The point is, will that dust shield work? Well, you'll be able to see the answer to that, as I said here, as the onboard impact sensors feedback second-by-second data on the kind of punishment that Giotto's taking. If the sensors themselves aren't destroyed, that is. Initially, that data and all the rest is coming in from space to a huge radio telescope in Australia and then to the European Space Operations Centre, Patrick.
Which is where I am now, at the headquarters of the European Space Agency. This is where the information from the comet is being received, but the real action's taking place over 90 million miles away. Here's the science area. We'll be meeting some of the principal investigators during the course of the night. And of course, there's the control room, which recently had the job of directing the spacecraft to its precise distance from the nucleus. But since the Russian and Japanese encounters, there's been a great deal of controversial discussion among the scientists here as to what that distance should be. We know that at the moment, Giotto is inside the coma, but outside the main dust area. What exactly is a comet? Basically, it has a nucleus, described as a dirty ice ball, which is the only reasonably massive part. When the ices are warmed, they start to evaporate, and the nucleus hides itself inside the head or coma, which is why we've never yet seen a cometary nucleus, something we'd like to rectify before this program's over. There are two types of tails. The plasma, or gas tail, is caused by the solar wind striking the comet's coma, the solar wind being a stream of electrified particles being sent out by the sun all the time in all directions. The dust tail is produced by the sun's light striking the coma and driving the dust particles outwards. And that's why comet tails always point more or less away from the sun. At the moment, Halley's comet is moving outwards, and so it's travelling tail first. The solar wind interacts with the cometary dust, and the solar wind is variable, gusty if you like, and this causes marked changes in the comet's tail. Giotto has already passed through the bow shock set up by the travelling comet, and we're getting ready for the main encounter. So let's consult the experts. What do they feel?
Well, I think this is the most exciting part of the mission. The spacecraft, of course, is now going to start seeing the dust. The instruments are now really going to start earning their money. The dust will start to increase significantly now, and we're starting to make the spacecraft wobble. So we hope we can maintain the signal, but at the same time we're hoping we can see the nucleus of the comet with the camera.
I'm hoping to see what the comet really looks like. So far, we've never really seen a comet. We've seen the dust cloud that envelops comets, and even those from a great distance.
We have preconceived ideas about the nature of comets. We believe that there's a comet nucleus in the center. We have some ideas about the origin of comets. We have worked for years on the composition of the gas and dusty atmosphere. We have pretty good ideas how much dust and gas to expect, but I'm sure there will be major surprises.
I am truly excited because it was 36 years ago that I first published my conclusions that the comet, the real comet, the nucleus, was made of ices and dust. And now we will be able to see what such a nucleus looks like.
Quite apart from the camera, Giotto carries many other experiments, most of them arranged on a necklace round the spacecraft. At the present moment, we can only speculate as to what a comet's made of. Giotto ought to tell us. We'll be studying the dust and the magnetic fields that are so important in tail production. We'll be looking at the chemistry and composition of the comet, its atoms, molecules, and ions, which are incomplete atoms. And then there are plasma studies. Plasma has been defined as the fourth state of matter, the others being solid, liquid, and gaseous. This is made of broken up pieces of atoms. But to demonstrate just what plasma is, let's go over to James Burke, or rather, see what James was doing in the courtyard of the old Royal Observatory a few hours ago when it was still daylight.
I'm doing it here in the freezing courtyard because, as you'll see, they didn't want to risk burning Greenwich down. Plasma, those broken up pieces of atoms that Patrick was talking about, make up about 90% of the universe. In this case, the plasma in question is caused by the solar wind, a cloud of superheated gas exploding at a million kilometers an hour out from the sun all the time. Now, the tremendous temperature of the sun strips the electrons from the gas atoms, and atoms without electrons are called ions. On board Giotto, the energy levels of those ions is being measured by a British experiment from the Mullard Space Science Laboratory. In essence, this is how the experiment works. This flame represents the hot gas plasma. And if you use this generator to send a charge through these plates and then through the ions in the flame, you can deflect the ions like this. Watch it being deflected to the left. It looks like wind, but in fact it's an electrical charge. Look, I'll do it again. And it's deflected. Now, if you measure how much charge causes how much deflection, you know how much energy the ions have, and you've measured the energy of the plasma. Now, that is basically how the plasma instrument on board Giotto works. This is where the plasma experiment sits on the spacecraft, and in fact it was switched on out in space some time back. The leader of the plasma analyzer experiment from Mullard is Alan Johnston. At his lab, he prepared his standby instrument for Giotto. This is the voltage generator. And these are the plates across which the electrical charge is applied. They're mounted on the particle detector itself. The plasma particles stream into the instrument and get bent towards the detector. Change the voltage, and you tune the instrument to measure the energy of different particles.
Well, some time ago, Giotto was hit by a huge shock wave. This is what it looked like on the computer printout. Let me stress that it didn't cause any damage because the density of the material is so low. Since then, within the last few hours, we've had some new information. Alan, what are your results so far?
Well, we've now been detecting the comet for more than 30 hours. We first found it at 4 o'clock yesterday afternoon, and it's gradually been increasing in intensity ever since then. And at about 8 o'clock this evening, we saw the first signs of the bow shock, and the bow shock turned out to be about 100,000 kilometers thick. And once we passed through the bow shock, we found, in fact, that it, instead of being more turbulent as I had expected, so far it's been quite a bit smoother, but hotter.
Well, you're using plenty of graphs. What exactly do they mean?
Well, we've got two to show on the screen here. This first one shows some of the different masses of ions that we're detecting in the comet. There's 4 frames there, each one taken successively, one after the other in time, and each one shows hydrogen ions and alpha particles from the solar wind in the bottom left-hand corner where it's red and green, and cometary ions in the top where it's blue. And one of the interesting things is that we're seeing particles at a mass of 8 where we didn't expect to see them.
How do you assess your results?
Well, they're very interesting. They're going to take a lot of analysing, but they're extremely interesting.
I imagine you expect better results from this as Giotto closes in toward the comet?
Yes, we're expecting things to change very rapidly in the next hour, and especially in the last 2 or 3 minutes just past midnight.
Alan, thank you very much. One thing that happens in comets is that the sunlight breaks up the molecules in the coma. Now, the comet's gravity is too weak to hold them down, so they start to drift away from the coma. Then they meet the solar wind, and they are hurled back into the coma. So one of the experiments carried upon Giotto is a detector to pick up these so-called energetic particles.
The Irish energetic particle detector is just here. It consists of 3 tiny telescopes collecting particles that are analysed by a solid-state detector at the back of each scope. Now, 2 of those scopes face sort of forwards, and the other one, well, it faces backwards. That isn't just an Irish way of doing things. It just doesn't matter which way you point when you're dealing with those high-energy particles. Moreover, many scientists didn't really think there'd be much call for such an experiment to measure them, so it wasn't originally going to go at all. But it is very small, it doesn't require any power supply, and it has a very persuasive Irish scientist who made quite certain it got on board.
How's the experiment going?
It's going very well. I'm pleased to tell you we have superb performance from the instrument.
What are you looking for?
At the moment we're looking for 2 things. We're looking for electrons which come from a hot plasma source associated with the comet. So they should come in puffs along the interplanetary magnetic field line when there's good connection between the comet and the instrument. So we'll be seeing those here. In fact, you can see some of the counts building up at this moment in those channels. And then another thing that we're looking for are pickup ions in the solar wind. You know that when the particles are ionized and become charged, they spiral around the interplanetary magnetic field line, so they can actually pick up energy from the solar wind.
And of course, if Giotto survives, you'll be able to go on collecting data on the outward journey.
Oh, well, that would be absolutely splendid, you see, because if that happens, then we'll see the pickup ions again on the other side, and we can go on observing for quite a long time, so the outward pass will be just as exciting as the inward pass.